Okay. Great. Okay, so I'm really delighted to welcome Professor Joseph Hennawi from UCSB, who will be chatting with us today at the Colloquium. So by way of introduction, Professor Hennawi did his undergrad at Stanford and then went to Princeton for a PhD, advised by Professors David Spergel and Michael Strauss on gravitational lensing of clusters, quasars, and the CMB. He then took a Hubble Fellowship and then an NSF Fellowship at UC Berkeley, and then spent 6 years at MPIFR as staff and then as a research group lead before taking his faculty position at UCSB, where he leads the Enigma group, which uses astronomical surveys to study the intergalactic and circumgalactic media. So logistics, tonight we're going to Henrietta's table for dinner at 5:30, so we'll be leaving here at 5:15, and if you'd like to join or meet with Joe today, please use the spreadsheet that's been circulated. And otherwise, today he's here to tell us about the hunt for a quasar lifetime measurement.
Great, thanks, Daniel. It's a pleasure to be here. It's my first time here at the Black Hole Initiative. Very impressed. So today I'm going to talk about quasar lifetimes, which is critical to our understanding of the formation of supermassive black holes. We've only known about quasars for about 60 years, but in the simplest picture, we expect their growth to take place over 50 million years. And because of the fact that we can't observe, humans have not been observing quasars for 50 million years, we're in the dark about how the black holes that power these quasars form. Since we have a small group, I want to encourage people to just interrupt, ask questions, not dedicated to getting through all my material. I think it would be more interesting if we had more of a discursive sort of presentation. So please feel free to interrupt. You can just shout out. Shout out to my collaborators who are shown here. In particular, I want to highlight the PhD students who did a lot of the work that I'm going to be talking about today. Okay, so brief outline. I'm going to give you a little brief introduction to supermassive black hole growth and the timescales that we think should govern it. And then I'm sort of testing this new phrase, quasar chronometry. Okay, so we're going to use physics that we understand to construct sort of cosmic clocks to time basically quasar activity. I'll present measurements from 2 of those methods, and then I'll discuss the implications for supermassive black hole growth, and then I'll summarize. So no presentation here at the Black Hole Initiative would be complete without this picture, of course, from the Event Horizon Telescope, a picture of the supermassive black hole at the center of our own galaxy, the Milky Way, about 1 million times as massive as the sun. And of course, it was the stellar dynamical measurements of this black hole's mass that were responsible for the 2020 Nobel Prize in Physics by Reinhard Genzel and Andrea Ghez. And not only are there supermassive black holes in our own, let me click on this. Little thingy? How do I do that?
We just hit the okay. No, you're good.
Okay. Yeah. And not only can we find supermassive black holes at the center of our own galaxy, but in our nearby galaxy M87, which is powering this jet, which is observed in the optical, and also another beautiful picture by the Event Horizon Telescope showing the variation of that black hole shadow with time.
I think you just need to click once.
Yeah, I think that's right. Did I lose my mouse? There we go. Okay. And we observe in the universe, right, in the local universe, at the center of every galaxy where we can resolve the stellar kinematics around black holes, we observe this correlation between the mass of the supermassive black hole on the y-axis and the velocity dispersion, or the mass of the bulge of these galaxies. So basically, these supermassive black holes are ubiquitous. They're at the center of every galaxy. And the question that we want to address today is, how did they get there, right? What process gave rise to them? And in the standard picture, supermassive black hole growth is directly related to quasar activity. Okay, so what are quasars? So it's a brief phase in the evolution of a galaxy, which is powered by the accretion of matter onto these supermassive black holes, which is actively growing those supermassive black holes. And during that phase, we don't actually see the galaxy light. The quasar way outshines the galaxy. It's about 1,000 times brighter than the galaxy. Okay, and the discovery of the quasar was in 1963. That landed Martin Schmidt on the cover of Time magazine. And immediately after these objects were discovered, given their luminosity and also their redshifts, which were interpreted in the then not completely accepted Big Bang cosmology picture, the only way to produce that tremendous luminosity is basically by accretion of matter onto a supermassive black hole. And so since I work a lot with observational data, no description of quasars as supermassive black holes is complete without showing you what they actually look like to an observational astronomer, right? So this is a spectrum of a supermassive of a quasar This is actually a composite, so we averaged spectra of sort of 50,000 objects between redshifts 0.5 and 3. Okay, and you can see from the spectrum that they basically look exactly like. We see there lots of emission lines from ionic metal transitions, which are basically responsible for cooling the gas around the supermassive black hole. But at redshift 7.64, this is the most distant known quasar. Okay, and I was involved in its discovery. And this is observed 670 million years after the Big Bang, right? And you can see that the basic spectral features look very, very similar. Okay, and then one thing that I'm not going to talk about in detail, but which is relatively crucial to our understanding of these objects, is that we can actually estimate the masses of the supermassive black holes that are powering these objects. And we do that by measuring the widths of emission lines, right, which are coming from gas that are basically gravitationally bound to the supermassive black hole. And that's a relatively established technique. We basically measure the emission line widths directly from their spectra, and then we use scaling relations that are well calibrated to measure their black hole masses. Okay, and so simplicity arises from complexity. Namely, we know that black holes have no hair from general relativity. They're actually just described by a few numbers, and that is why maybe they're so intriguing, right? Because the description of that space-time is so simple. But the actual physical process of supermassive black hole growth is a complex systems problem. Okay, so even though the end state is extraordinarily simple, the growth is incredibly complex, right? And if you just sort of work out some numbers for the sort of physical length scales that you would need to basically describe, right? You're talking about, at the gravitational radius, right, where the event horizon is, you're talking about light hours, right? But then if you want to really understand how they're fueled, maybe you need to think about or resolve, galactic scales, which are sort of 10 to the 4 to 10 to the 5 light years, but then to place them in a cosmological context, because these objects, particularly at early cosmic times, are so rare, then you need to think about 10 to the 10 light year cosmological volumes. Now, these are the sort of naive estimates of the numbers. There are, simplifications that you can use to numerically try to capture this phenomena. But the bottom line is that the reason why we don't understand how supermassive black holes grow is because there's this crisis of dynamic range. Okay, in order to really have a first principles ab initio picture of this, you would basically need to be resolving cosmological scales or describing galactic and cosmological scales, but also scales of the order of the gravitational radius and the accretion disk.
Can I ask a question?
Yes, please.
So can you also measure the spin and the?
You can measure the
Or is it
spin.
more difficult?
You can measure the spin from gravitational waves, right? So mergers of black holes, not supermassive black holes yet. Okay, but for stellar mass or 10 solar mass black holes, you can measure the spins from gravitational wave measurements, and that's a relatively new and also Nobel Prize winning phenomenon. Okay, so how do we go about this, right? So as I said, it's a complex systems problem, okay? And so we're physicists, and so we like to think about the world in an ab initio sort of causal way, right? So then you would like to load up some kinds of initial conditions on a computer and then evolve the system forward in time. Right? And that is an important framework for building intuition and interpreting observations, right? But because of this crisis of dynamic range, then, there are going to be some issues. You have to make assumptions, right? You can't simulate the whole physical process. And so usually what those assumptions boil down to is that you make subgrid approximations for things that you don't resolve with your hydrodynamical grid. And that usually then involves models that have a tremendous amount of flexibility with tunable parameters. And so then the robustness of conclusions from these simulations is not always completely clear. You're certainly learning something in the framework of a particular calculation, but the degree to which you can generalize and actually convince yourself that you're learning something robust about supermassive black hole growth, as I say, is not always clear. And so this little physics reliability meter is going to come up a lot during the talk, okay? And I'm going to sort of grade the physics that's being invoked. Or described at various moments. And if you have questions about the reliability of anything, please feel free to ask. Okay, so I'm giving an orange grade to these ab initio simulations. Again, I'm not making necessarily a normative statement about how valuable they are. I'm just trying to let you know, we have to make judgments about what is speculation and what is absolutely robust. That's just a part of being a physicist.
Can you say maybe a specific simulation you're rating in this way?
Well, so yeah, I'll come to that during the talk.
Okay, I just wasn't sure if
Yeah.
okay.
Yeah, that's a fair question. Yeah.
Are you questioning the premise of GRMHD? Would that go in this?
I'm gonna come to that as well. Yeah, I'll come to GRMHD. Thanks for that question.
But this is specifically about the subgrid and.
I'm just saying in general, right? So if I had to, so this is a little bit of a generalization, but there's a whole hierarchy of scales. And there's a whole hierarchy of strategies for doing these kinds of calculations. And maybe it's not completely fair to give them all orange, okay? But later on in the talk, I'll give you some more. So I'll break it down a little bit better. Okay, so then what the approach that I'm going to take is that I'm going to remain agnostic and we're going to just try to proceed empirically. But importantly, I'm going to leverage physics that we absolutely understand, which comes from our precision cosmological theory of the universe, right? So I'm a cosmologist. I'm studying objects at cosmological distances, and so I'm going to leverage cosmology. And that physics that we're going to use to construct these clocks is actually bulletproof for the most part. Okay, and feel free to ask me if you don't agree with that. Okay, we're going to just try to focus on a simple question, right? Which is, what are the timescales that govern this physical process? So then this comes from a simulation, right? And this is an example of like a supermassive black hole growth history or a quasar light curve, right? So I'm showing you the ratio of the total luminosity emitted by the accretion disk around the black hole as a function of time, which is directly proportional to the supermassive black hole growth rate. Maybe it looks like this, maybe it looks like something else. And we're just going to try to figure out, can we actually constrain this light curve? And then what kind of insights is that going to lead to about supermassive black hole growth? Okay, so this is the textbook picture of supermassive black hole growth. It's very, very simple, okay, but also very, very useful in terms of building intuition, right? So you have material that's flowing onto a black hole, right? That's some initial condition on larger scales, which is this accretion flow. Okay, rest mass energy is basically falling onto the black hole. And some of that material is going to convert its gravitational potential energy into kinetic energy. That's going to then be thermalized, and some fraction of that rest mass energy is then going to be radiated as our quasar. That was the spectrum that I showed you. So that's going to directly result in the quasar light that we observe. That's what's known as the radiant efficiency, right? And so, however, there is an important point, right? Which is that radiation, of course, exerts a radiation pressure, in this case, due to Thomson scattering. There's no way to get around that. And that radiation pressure, right? If the quasar is growing fast, right? It'll be very luminous. If it's very luminous, it's going to exert more pressure on the material. And at some point, you will unbind the gas because of this pressure. So you will halt the accretion flow due to radiation pressure, right? And that this critical luminosity, which is known as the Eddington limit, right, is basically just where radiation pressure directly balances the attraction of gravity, right? So it's proportional to the black hole mass. And then we can just simply rearrange this calculation, this equation, and you basically get that supermassive black holes, if they're accreting with a certain radiant efficiency, right, and with a luminosity that's some fraction of this maximal luminosity, which is the Eddington limit, should just be exponential. And the characteristic time scale is what's known as the Salpeter time, which is 45 megayears, plugging in our best guesses for what these numbers are, the radiant efficiency and this Eddington ratio, okay? And then there's this seed mass here. You start from some seed black hole, which is a stellar remnant, and that could be, for example, early star in the universe known as a population 3 star that then collapses under its own self-gravity. And the standard number that people use for that would be 100 solar masses. Okay, so 100 times the mass of the sun, which is the mass that you expect those early black holes to be at. Okay, so this is really, really simple physics. Okay, but then the question is, well, like, where does the radiant efficiency actually come from? Okay, and again, you can see on the physics reliability meter, it comes from general relativity, right? And the idea is that there is, of course, this innermost stable circular orbit, right, in whatever metric you're working in. Okay, and at the innermost stable circular orbit, yes?
This is a dumb question. At what point does it stop growing? Is
Uh,
it just an exponential or do we change at some scale?
I mean, so you're asking really, I mean, right, so I'm just assuming that there's some fuel supply. Okay,
Oh.
and so whether or not it continues to grow is going to depend on this fuel supply, but under the presumption of this fuel supply, this is the maximum, you know, this is the maximalist picture, and this is the characteristic time scale. Make sense? Yeah.
So these are heavily accreting black holes. These are not like your M87s.
No,
Or Saturday
this is the quasar phase is the active phase of supermassive black hole growth. So this is when the Sagittarius star, the M87, this is how it got to be, we think, as big as it did. That is the standard picture, and I'm going to come to that equivalency in just a minute. Okay, so now, right, in GR at the innermost stable circular orbit, there's just your kinetic energy is just some fraction of your rest mass energy. For a Schwarzschild black hole, that number is 10%. Okay, and if the black hole's spinning, it could be even larger, right? And basically you have that kinetic energy, there's some accretion disk, you're going to thermalize that kinetic energy due to viscosity, right? And then that accretion disk is going to basically radiate away that thermal energy, and that is the quasar light that we see. Okay, and so that's the simple picture, which comes from GR, right? Very simple physics. But accretion disks are actually a lot more complicated, we think, and I'm going to come to that in the next slide. Okay, and so, like, why should it be that, like, this, you know, undergraduate picture of a black hole actually holds for setting this radiant efficiency if in fact there's a very complex physical process underlying? Okay, and this comes to the question that you had, and you notice that I'm giving these calculations a higher reliability, right? So these are magnetohydrodynamical simulations of accretion disks, right? So this technology has sort of gotten to the point where you can actually simulate, do a global simulation of a black hole accretion disk. And so what sets this viscosity that thermalizes that kinetic energy and is ultimately responsible for the radiant efficiency is the detailed magnetohydrodynamical structure of this accretion disk. Okay, and these simulations are, you know, not yet super mature, but the point is that, like, generically, they sort of indicate that this radiant efficiency could actually be quite small. So what does that mean? You're not achieving the GR limit of 10%, right, where you convert all of that kinetic energy into essentially thermal energy. What's actually happening is that you're advecting both material and radiation onto the black hole, and so you're not actually radiating that much. Okay, and so then, you know, this simple exponential picture of growth need not apply, right? Because there's a lot of other things that could govern the timescales or the light curve, right? So, like, galaxies merge. And when galaxies merge, tidal forces could trigger inflows towards the center of the galaxy, possibly being responsible for this fuel supply that we talked about. And that timescale is going to be gigayears, right? And then there could be other secular processes going on in the galaxy itself, right? So you might expect that on a galaxy dynamical timescale, this fueling could change, and you could go from some active quasar phase where you're actually accreting a lot to some more quiescent phase where the fuel supply is somehow halted, and maybe that would occur on the galaxy dynamical timescale. Okay, so those emission lines that I showed you in the spectrum of the quasar actually originate from a region known as the broadline region, right, where the broadlines come from, and this is a schematic diagram. That scale is something like a parsec, okay? And you know, in the broadline region, the dynamical time, so we've measured the sizes of these broadline regions locally, right? And we know how fast things are moving because we measure the line width, so then you can work out a time scale, and that's going to be sort of 100 to 1,000 years, right? And then you could talk about the accretion disk itself, right? The light that we see coming from that accretion disk is coming from something like 150 RG, and at 150 RG, the dynamical time is something like a year. Okay, and so you might expect, so we don't really know, like, what is the important time scale? Is it cosmological? Is it galactic? Is it related to the fuel supply in the broadline region? Is it on the accretion disk scale? We don't know exactly what the important time scales are. Okay, but if you just work out dimensional analysis, from dimensional analysis, basically just using Kepler's law, and the fact that everything is going to scale according to RG, which is just proportional to the mass of the black hole, then essentially all the time scales in the problem just scale as the mass of the black hole, okay? So this is a light curve of what's called a microquasar, right? So it's a 15 solar mass black hole in our galaxy. It's not a supermassive black hole, and it's not at cosmological distances. It's actually in our galaxy. But because the black hole is small, it emits all of its radiation in the X-ray. Okay, and you can time X-rays very well, and this is what the light curve looks like, and you can see that it's varying on time scales of like an hour, right? And if you just scale things up to 5 times 10 to the 9 solar masses, which is more typical of the supermassive black holes that I'm going to be talking about, I should emphasize that the physics of the accretion disks in both this 15 solar mass black hole and this supermassive black hole is believed to be the same underlying physics, right? And it's the same general relativity that describes everything. So then you're going to get that if you just do that simple dimensional analysis and then scale up the time axis, you're going to get time scales of something like 1 year to 10 to the 5 years, right? So that this could be actually what's happening if we just use objects that we believe we understand. Okay, and so now a very important argument is called the Soltan argument, which is basically a demographic argument. Okay, so this is going to be very important. It's going to come back later in the talk. So please ask me questions if you're not following, right? So we can just count up the quasars that we see in the universe, right? So we can just count them all up. That's pretty easy. It's just counting shit, right? Like how hard is that? You go out there, you conduct a survey, you measure some redshifts, you count quasars, you do this luminosity function. It's a double power law in many redshift bins. Okay, and you have a description of the quasar population as a function of cosmic time. At the same time, so that's in the distant past, but then locally, I know that black holes follow the scaling relation with the galaxy velocity dispersion. So I can count up the nearby galaxies in the universe. I measure their velocity dispersions, which is very easy. And then I use the scaling relation to figure out how massive all their black holes are, right? And so then what we get is this commensurability, which is essentially just a statement of conservation of mass energy, right? So there's some luminosity in these quasars divided by the radiative efficiency gives me the total amount of black hole mass that I've grown. So that's this side of the equation, right? So this is the energy emitted by all quasars over cosmic time, okay? And that energy that was emitted directly resulted in supermassive black hole growth, and then it has to equal to the local population of black holes that I observe at redshift 0. So then this is an integral over the black hole mass function just using these scaling relations. Then I get a mass density of supermassive black holes today, right? And if you equate these two, the only thing that you don't know is the radiative efficiency, right? Because that is what turns light into mass, okay? And so what you get when you do this, surprisingly, is that you get 10%, which is consistent with the super simple picture of general relativity, right? So like I tried to convince you that real accretion disks could be very complicated, right? But when you apply this integral constraint, right, you get 10%, which is just GR. And that's sort of the accepted picture. Okay, and if you think that's weird, I agree with you. Okay. Okay, and then I'm giving this a perfect score on reliability because it's really just conservation of energy. You can quibble about the measurements and we'll come back to that later, but like I said, it's essentially just counting things. Okay. All right, so then there's a challenge for these super high redshift supermassive black holes that I talked about, right? And the challenge is that we see them just 700 megayears or so after the Big Bang. And so if you invoke this maximalist picture of exponential growth, which just presumes that you have a fuel supply, right? If you invoke that and you say, but I can accrete faster than the Eddington limit, right? But then that means I grow exponentially on a time scale of 45 megayears, subject to this radiative efficiency, which governs that time scale, right? Then, you know, things just grow exponentially. So if I measure a black hole mass of 10 to the 9 solar masses in a redshift 7.6 quasar, which is this red point here, then if I run it back in time, assuming that I started at some point in the early universe, it's not that sensitive to when you assume, because basically all the time in the universe is basically at later times, okay? Then you basically have this problem that like, you can't grow them from these population 3 stars that you think are the seeds of the black holes, right? You actually have to invoke much more massive seeds, right? So where these curves, so if you think things started at redshift 30, which is typically what people assume for say a young galaxy in a population 3 star, then you need the seed to be 10 to the 4 solar masses, okay? And so then that leads to all of these speculative ideas about these exotic mechanisms for forming these seeds, direct collapse black holes. So you have something on galactic scales that just directly collapse to form a black hole of 10 to the 4 solar masses. There are other ideas out there about the collapse of a dense star cluster, et cetera, et cetera. Okay, so that's a problem. It's the supermassive black hole growth at early times problem. Like there's just not enough cosmic time to grow the supermassive black holes that we observe in these distant quasars. Okay, and so one solution would just be to allow the radiative efficiency to be smaller, right? If it's smaller, then the time scale is much shorter, and then I don't have a supermassive black hole growth problem anymore. Okay, but then you can't really do that everywhere at all cosmic times, because then you're going to break the Soliton argument and the conservation of energy. Okay, so and I should add that like a lot of theoretical work is being dedicated to thinking about these massive seeds, right? And like if you have physics training and you look at this equation, you're like, wait, I'm linearly proportional to the seed. I'm exponentially sensitive to the time scale. So why is everybody focused on the seeds? And I don't actually know the answer to that question. I think it's because talking about these seeds is more fun and it's easier. And like doing these accretion disk simulations is like really hard. Like you got to eat your vegetables and do difficult magnetohydrodynamical simulations. And so for some reason, theoreticians are spending a lot of time working on these seeds, and there's really no evidence for them except for maybe this problem. Okay, so that's but we can come back to that later during the discussion. Okay, so quasar chronometry. So the first clock that we're going to construct is using the intergalactic medium. Okay, and so in order for me to explain to you about the intergalactic medium, I've got to teach you a little bit about cosmological structure formation. But before that, I just want to be clear about an assumption that I'm going to make. Okay, so I'm going to replace this complicated potential growth history of the supermassive black hole with a very simple light curve. Okay, it's just going to be a light bulb light curve, right? Supermassive black hole turns on at some time, like a light bulb, shines for some amount of time we're going to call TQ, which is the quasar lifetime, and then it turns off. Okay, and that exponential growth, on timescales comparable to the Salpeter time is going to be reasonably well approximated by this light bulb. Okay, it's not a perfect approximation. It should be improved. Most of what I'm going to tell you about today isn't tremendously sensitive to this assumption, but obviously I'm not going to be able to constrain that full light curve, so I'm going to sort of constrain its 0th moment. Okay. Okay, so when I talk about the quasar lifetime, I'm talking about this light bulb light curve. Okay. So we're very good at simulating structure formation on cosmological scales. All right. Why is that? Well, we get the initial conditions of the universe from the cosmic microwave background. We know that the universe is 30% by energy dark matter. And sort of puzzlingly, or maybe confusingly, even though we have no idea what the dark matter is, there's lots of evidence that it's basically just cold collisionless particles. Okay. And the only force that you have to deal with is gravity. And so even though we have no clue what the dark matter is, we can actually load up those initial conditions onto a computer, which we've measured very precisely, and we can evolve the universe's structure forward in time because we know that the properties of dark matter have to be simple. Okay, and then you basically get this cosmic web of gravitational structure. This has been tested at the percent level. Okay, and so this is very, very robust physics, and we're going to leverage this physics at various points in the talk. But basically, cosmic structure formation isn't something that I really want to have a debate about, because that would put you into the realm of crackpots. Okay, so this is very, very well established and very, very, very well measured physics. Okay, what about the baryons, though? I'm showing you the dark matter. What about the baryons? Okay, so the baryons are actually just kind of along for the ride, right? So by mass energy, 5% of the material in the universe is baryonic, 70% is dark energy, and something like 25% is the dark matter that I just showed you in that simulation, okay? And so for the most part, it's just neutral hydrogen that's just tracing this distribution of dark matter in the universe. That's what's called the intergalactic medium, all right? And it's at very low density, sort of 1 atom per cubic meter. And this hydrogen is just tracing the dark matter in the cosmic web. And we've made, as I'll come to, also percent level measurements of the distribution of hydrogen in the intergalactic medium. And we're very much convinced that this picture is correct. Okay, cosmic reionization, all right, which I'm going to invoke for one of these clocks. Right, so in the beginning, there was the Big Bang. The universe was a hot ball of ionized plasma, right? It expands and cools, a period known as the cosmic dark ages. At some point, right, the universe is actually cool enough for the first atoms to form, and that's what's known as the recombination phase transition, which releases the cosmic microwave background in all directions of the universe. At that point, you just have, sorry, the universe is I misspoke. The universe is a hot ball of ionized plasma. At some point, you form atoms, okay? That's when the CMB is released. And then you just have a neutral gas, okay? But meanwhile, galaxies and possibly black holes are forming. Stars in those galaxies are going to emit ionizing photons. And eventually you're going to build up enough ionizing photons to re-ionize the universe and convert it from a neutral gas into an ionized gas with a neutral fraction of 1 part in 10 to the 5. Okay? This is an active area of research. Okay? I'm giving it a yellow on the reliability scale. This is a movie showing what that might look like. Okay, where the topology that you see in blue is becoming ionized, and the dark regions of this topology are the neutral regions, right? And so, like, the details of this process aren't very clear. We have constraints on the timing of reionization from the cosmic microwave background and other probes. And we think we know what the topology of reionization is because we know what structure formation does. It gives you this cosmic web. So we think we understand reionization reasonably well enough, but this is an active area of research. Okay, the way that we study the intergalactic medium is actually also using quasars. So quasars are cosmic lighthouses at cosmological distances. They emit ultraviolet radiation. And as that ultraviolet radiation propagates through an expanding universe, it gravitationally is going to redshift away its energy until it actually redshifts into the neutral hydrogen resonance. Okay, and when it redshifts into the neutral hydrogen resonance, it'll be absorbed at that location. Bluer light will get absorbed after traveling a larger distance. And so at the end of the day, what you get from a quasar is this so-called Lyman alpha forest, this forest of absorption lines, which, because you're observing the quasar through an expanding universe, is actually giving you a one-dimensional probe of the neutral hydrogen gas and the density field along the line of sight. Okay, and this is how we know that the intergalactic medium has the structure that's predicted by our cosmological model. Okay. So one challenge, though, for understanding reionization, and also, as we're going to come to measuring the lifetimes of these quasars, is that this overly sensitive Lyman alpha transition can't actually probe a highly neutral medium. The Lyman alpha transition is actually just too strong. So this is the quasar at redshift 0.3. This is one at redshift 3. This is one at redshift 6.3. Okay, and you can see that you observe these rare absorption lines at low redshifts, but then at high redshifts, it's like this Lyman alpha jungle rather than a forest. The regions are just completely absorbed. And you might think, well, that means that the universe is neutral, but you only need a neutral fraction of 1 part in 10 to the 4 to basically completely make this sightline opaque. So for that reason, you can't actually, the reason why this is actually getting thicker isn't because the universe is per se going through the reionization phase transition. It's actually just because the universe is getting denser at earlier times when it was smaller. Okay, and so if you want to make statements about both reionization and quasar lifetimes, you need to focus on this interface between the quasar itself and the intergalactic medium, which I'm going to call a quasar proximity zone. Okay, so now imagine I've got a quasar in a reionizing intergalactic medium. Black regions are ionized and white regions are neutral. Okay, so the quasar is starting out in some ionized region, and we're observing it here through this possibly high column density of neutral material. Okay, and the beauty of the Lyman alpha cross section is that it actually has these Lorentzian wings due to the actual, the lifetime of the atomic state, right? So these damping wings, this is the natural width of the Lyman alpha cross section. And these damping wings, if you have a large enough column density of material on the line of sight, actually give rise to this smooth damping wing absorption that we observe in absorption lines all the time. That's just a picture from an interstellar medium textbook. Okay, but the point is that if you have enough column of neutral material along the line of sight, then you're actually going to imprint a damping wing on the quasar spectrum. Okay, and that might look something like this. Okay, so this is a simulation of a quasar. Okay, there's some ionized region around it due to the quasar's own radiation. I'm going to come to that in a minute. That's what's known as this proximity zone at the interface between the quasar itself and the intergalactic medium. And I'm going to start out with a neutral fraction of 1%, and then I'm just going to run the movie, and you'll see that as you crank up the neutral fraction of the medium, you eat away at this over-ionized region near the quasar, and you imprint this smooth absorption along the quasar's, I call it the continuum, redward of the actual resonance due to that damping wing. Okay, so you're basically seeing the damping wing imprinted on the quasar spectrum. Yes,
So all of these absorptions are local, you're saying, the one to the left, or?
they're
or
intergalactic.
they're intergalactic.
So this is like 10 megaparsec scales or something. So these are in the intergalactic medium. That's an important question because we actually know what this structure should be. Okay, because we have this precise understanding of cosmic structure formation in the intergalactic medium. So they're not local to the quasar galaxy or to the quasar itself or to the accretion disk. They're actually occurring on cosmological scales. That's a good question. Okay, so that's not the whole story though, right? Because the quasar itself is a very luminous source and is emitting a tremendous number of ionizing photons. And so it's going to carve out its own ionized bubble. It's going to start, maybe the quasar turns on in some pre-ionized intergalactic medium, but then it actually carves out its own ionized bubble. And that's what's giving rise to these absorption lines, because otherwise the intergalactic medium would be too opaque. Okay, so this is the critical point of this clock. Sorry. Is that the neutral intergalactic medium is actually an ionizing photon counter, okay? Because you're going to ionize some bubble of ionized material around the quasar. And, in the simplest picture, we actually do this calculation more rigorously, right? But you just count the number of ionizing photons, and that's the number of atoms that you've basically ionized in the bubble, okay? This is a cosmological ionized region powered by the quasar itself, right? But the number of ionizing photons is just the integral over the quasar light curve, that thing that I was showing you before, over all of cosmic time, okay? So that's proportional to the quasar's luminosity. The quasar's luminosity via the radiative efficiency is proportional to the accretion rate or the growth history of the black hole. And so if you just integrate both sides of the equation, then you basically get the total number of ionizing photons that you emit, okay, is just equal to or proportional to the total supermassive black hole mass that you grew. Okay, I'm not saying anything controversial here. And so this sounds a lot like the Sultan argument, right? But rather than applying it to the universe as a whole, it's like a local Sultan argument. There's this island universe, which is basically the quasar. It's emitting ionizing photons. And because of the fact that the recombination time in the intergalactic medium is longer than the age of the universe, every photon that's emitted just basically moves this ionization front outward, okay? And the beauty of it is that this ionization front is something that we can observe using the damping wings that I just showed you, right? So then essentially what it boils down to is that we can measure the black hole masses from the quasar emission lines. I can measure the total number of ionizing photons that were emitted from the proximity zone and the damping wings. I can localize this ionization front. And then the only thing that I don't know is this constant of proportionality, which is the radiative efficiency. Okay, so it's like a single object Sultan argument, if you will, which is
Say again, I'm sorry, why the width of the absorption wing is proportional to the column of
sure.
of neutral hydrogen?
So basically like, yeah, so there's an optical depth.
Right.
The optical depth is the integral, is basically the column density times the cross section,
Mhm.
okay? And if you have a small column density, you just observe the core of the line. And if you have a really large column density, then the core of the line is completely saturated, and then you generate the wings. So the more material you have in the foreground, the stronger the wings are. Does that answer your question?
Yes.
Okay. Okay, so then now we just went through all that. So now let's watch the same simulation. Now I've just turned I've set the intergalactic medium to be totally neutral. Okay, so this is like the maximalist case. And then I'm just gonna change the quasar lifetime, which is effectively the same thing as just changing the total number of ionizing photons emitted. So we're gonna watch how this proximity zone changes as a function of time. So if the quasar lifetime is super short, right, then you just see this absurdly strong damping wing with no proximity zone, no absorption lines. And if you let the quasar shine longer, right, then you see that the damping wing gets a lot weaker, right? Okay, it's getting weaker and weaker, and then these absorption lines due to the proximity zone start to appear. And you notice that around a Salpeter time of 45 megayears, right, then there's basically hardly any damping wing at all, right? And the proximity zone is huge. Whereas if the quasar lifetime is much shorter, the proximity zone isn't there and the damping wing is super strong. Okay, so that's our cosmic clock or our quasar chronometer that we're going to use. Yes,
If the quasar is flickering, what's the recombination timescale?
it's longer than the age of the universe.
Oh.
So that's critical to this argument. Okay, so I'm not in the Stromgren sphere limit, which is ionization equilibrium. I'm in the transient phase that you never observe in the galaxy around an O star. I'm basically in the regime where because of the fact, it's just like there's no photon left behind. I catch every photon. Right, so like it doesn't matter whether you had 2 quasars there or 10 or 1, every photon that's emitted in my direction I catch because the universe is optically thick and the recombination time is longer than the age of the universe. It's actually like at really long lifetimes it becomes comparable to the age of the universe, but we model that, right? So we're doing this calculation. I'm not using these equations in the actual calculations. We do full radiative transfer simulations. Okay, so that sounds great, except for there's one important thing I left out, right? Which is that we don't actually know this curve. Okay, if I knew this curve, this would be a pretty easy thing to do. Okay, but I don't actually know the underlying unabsorbed continuum of the quasar because that's some messy thing that has to do with like the broadline region of the quasar. That's its own stochastic process. The intergalactic medium is a stochastic process, the topology is a stochastic process, and this unknown quasar continuum is also a stochastic process. It's a nuisance stochastic process. Okay, so then what we do, and I'm happy to provide details later, but I'd rather just cut to the punchline, but please do ask me questions if you're interested in the methodology. This is what I spend most of my time on, okay, but probably the least interesting topic for this crowd, okay, is basically I use the fact that quasars aren't really snowflakes, okay, they're actually snowflakes that obey correlations, okay, so we basically take the quasar, this is a mock spectrum that we use to calibrate our inference procedure, okay, so I've created a simulation of a quasar spectrum. There's this green curve, which is the true continuum of the quasar, which I don't know. That's this nuisance stochastic process. We use dimensionality reduction to describe that, okay, because there are correlations between these lines. So if I know what the red part of the spectrum is, I get pretty good knowledge of what the blue part that is being absorbed away looks like, okay? And then we can't, dimensionality reduce perfectly, so there's some noise in that. That's a continuum error stochastic process. And then the Lyman alpha transmission and the reionization topology is another stochastic process, which is a cosmological one that we understand how that varies with certain astrophysical parameters like the neutral fraction of the intergalactic medium and the lifetime of the quasar. Okay, so then what happens is then you basically use machine learning techniques. Okay, actually, the only real machine learning technique that we use is basically being able to do fast Markov chain Monte Carlo, which is called Hamiltonian Monte Carlo. The dumbest dimensionality reduction that you could think of, which is just principal component analysis, actually works better than machine learning. But we use some machine learning-like techniques, and we run this on thousands of mocks to basically validate that our technique works. Okay, and here's an example on a mock where the blue curve is basically our estimate of what the true underlying continuum is. The red curve is our model fit to the spectrum. There are 6 or so parameters that describe the quasar continuum nuisance process that we marginalize out. And then at the end of the day, we get contours that look like this with, let's say, the 2 numbers that we care about, the neutral fraction of the intergalactic medium, which we also don't know, okay, and then the lifetime of the quasar. And you see here that we're able to measure the lifetime of the quasar here to about 0.8 dec. It actually depends on where you're at exactly in this parameter space. Okay, so that was mocks. Let's see what this looks like on real data. Okay, so these are spectra of 2 distant quasars that have been observed with the James Webb Space Telescope, one at redshift 7.5 and one at redshift 6.8. So this is like squarely in the period where we believe that the universe is undergoing this reionization phase transition. Okay, and then this is our modeling machinery at work. Okay, So I don't know what the true underlying quasar continuum is, but that's our estimate of it, which is the blue curve. The red curve is the model fit, and you can see that the model is fitting the quasar spectrum very well. Okay, and then these are the values that we infer for the neutral fraction and the lifetime of the quasar. So it's this two-dimensional parameter space that we work in after we marginalize out the nuisance parameters. Okay, and what you can already observe here, right, by looking at these two examples, is like one quasar has like a really long lifetime, sort of on the order of the Salpeter time of 10 to the 7 years, and another one has got a very short lifetime of 10 to the 4 years. Okay, and so then if we put this all together, right, so I've analyzed a sample of 41 of these objects, okay, from redshift 5.7 to 7.6 when we think reionization is occurring. All right, and then each one of these violins is the posterior distribution for the lifetime. Okay, so the first thing is there's a lot of variation in these lifetimes from 10 to the 4 to 10 to the 8 years. And then the other thing that you see is that if we put all these values together, we can sort of fit a log normal distribution. And that log normal distribution is 10 to the 6.8 years in the log of the lifetime as the mean. And then there's a sort of a dispersion of about 1 dec. Okay, so we'll come back to that. Next, yes.
There's one step that I missed. So you said earlier that this proportionality between the delta T or the delta M, the mass increase.
Yeah.
And the ionizing photon number is proportional to the epsilon, right?
It's
To
the epsilon, right?
So did you assume 10%?
No, I'm actually not. So that comes later. So I'm basically measuring the number of ionizing photons here. I'm phrasing it as a lifetime, but if I use the luminosity of the quasar today times that lifetime, that's the number of ionizing photons. So this is I'm gonna come back to this, but this is you can think of this as a measurement of epsilon. Okay, I'm gonna need
Can
Yeah.
we go back to the spectrum plot, the fitted spectrum plot? Yeah,
Yeah.
here. So the black curve is the observed one.
is the
right?
observed one, yeah. And the red
Yeah.
is the fit and the blue is the unknown.
So the red curve should kind of be close to the black one, right?
Right.
So is there any specific reason why it's like always below the black one on the bottom?
Well,
part?
everything's correlated. It's all covariant.
Mm.
Right? So that's what these matrices are. And so it's all correlated. They're pretty good fits. And we've tested this on 1,000 mocks. I'm gonna speed ahead because I'm kind of running out of, I want to get to the second probe and the punchline, but please ask me again about that later. Okay, so another cosmic clock that we can use leverages the cosmic web. Okay, so basically we know the abundance of these dark matter halos from these cosmological simulations, and we also know how they should be clustered on the sky. Okay, and this is very, very, oops, that's not the right reliability meter. This should be green. Sorry, I think I screwed up when I was cutting and pasting, but this is bulletproof physics. Okay, and so then the way that this works is that this is a completely independent probe of quasar lifetimes, right? So the gray circles are dark matter halos, okay? And then the stars are meant to be the quasars that are on at any given moment, okay? So quasars temporally subsample their dark matter halo hosts. But if you subsample a population randomly, you don't change its distribution of clustering on the sky. Okay, it's the same underlying dark matter halos. They should be clustered in the same way. You're just randomly subsampling them in time. Okay, so if I can measure the clustering of these objects, which I'm describing here with this correlation length, okay, which is basically where these correlation functions, which measure the deviation from random clustering, where this correlation function is equal to 1. Okay, if I can measure the clustering of the quasars, right, then I basically know the masses of their dark matter halos because the clustering of a population doesn't change if it's subsampled. If I know the masses of the dark matter halos, those same simulations tell me the abundance of those dark matter halos. Okay, so then the idea is that the quasar hosts are in green, only a fraction of them are shining at any given time, okay, which are basically the stars, right? But then I can basically measure this number density of their hosts, that's the denominator. I can simply count up the number of quasars on the sky, which is the numerator. That's equal to what's called the quasar duty cycle, which is the fraction of the Hubble time that the quasars are on, okay? So totally independent lifetime probe, but also leveraging our precise understanding of cosmology, okay? Okay, so the James Webb Space, ooh, what happened?
Just wait a second, we'll come back.
Keep cool, stay calm.
It's
stay
a
calm.
miracle.
Okay, so the James Webb Space Telescope has proven to be revolutionary for measuring the clustering of objects, galaxies, in this case is the tracer population that I'm going to use around the quasars. Here's an image from the James Webb Space Telescope, but it also has a mode where you can put a dispersing element, okay, basically a grism into the beam, and then you basically just disperse that image. This is called slitless spectroscopy. Okay, so you get a spectrum of every object in that image. So here's an example of a spectrum of the quasar itself. Okay, these are the broad emission lines in the broad line region of the quasar, right? That's where the quasar is. Here's a galaxy at the same redshift as the quasar, which is clustered around it. And we use these emission lines to basically identify the locations of all those galaxies, right? And then the idea is that you can measure the distribution of galaxies around a quasar, around a population of quasars. So here's an overdensity of 12 galaxies that are around the quasar indicated by the red arrow. Okay, good. So then what you do is you rely on cosmology, which again is very, very robust, and you measure the clustering of the galaxies themselves, okay? That's the blue curve. You also measure the cross correlation, so the average overdensity, if you will, or the overdensity profile of the galaxies around the quasar. That's the orange curve. This is the sample that we observed. We see a lot of variation of the overdensities around the quasars. That's actually expected. It's called cosmic variance. The universe is a stochastic process. Okay, and this agrees well with an independent measurement that I was also involved in for 5 objects at a slightly different redshift. Okay, so now we've measured that quasar clustering. Then what we do is we basically model this signal, okay? And the only thing that we don't know is how the quasars and the galaxies are actually distributed over the dark matter halos in the cosmic web, right? And we're able, because those measurements are so precise, to constrain both of those distribution functions very well. And as I said, if you know this one, right? So this is the distribution of quasars as a function of dark matter halo mass. This gray curve is the underlying population of dark matter halos. So this difference is the duty cycle, right? It's just the fact that at any given time, not all the quasars are populating their hosts because they're temporarily subsampling their hosts. And so if you do this, you get a lifetime of 10 to the 6.5 years. Okay, so then this is the money plot, okay? I've got 2 very, very different probes that both leverage physics that I would argue is very, very robust. And they're both telling us that the quasar lifetime is something like 10 to the 6.5 years, okay? Whereas the characteristic timescale that you would expect these quasars to be shining at their current luminosity, given the standard picture of supermassive black hole growth with a radiative efficiency of 10%, is something more like 200 megayears, because they're not actually all shining at the maximal Eddington rate. They're shining at 1/4 of the Eddington rate. Okay, so the point is that these quasars are shining for timescales that are far lower than the characteristic timescale on which you expect them to grow. And so, WTF? What's going on? Right?
But
Why?
How certain is that factor of 50? 50 doesn't seem like a lot.
So I think the argument is relatively clean in the sense that we actually phrase it in terms of the number of ionizing photons, and you get something like a factor of 50. There are some assumptions here, okay, that I'm happy to talk about later. But we're basically essentially I have an integral constraint on the light curve in both cases. The duty cycle and the proximity zones are an integral constraint. So I can just phrase that as the total number of photons emitted, and then divide that by the radiative efficiency. That gives me a black hole mass, and that black hole mass is 50 times smaller than the black hole masses in the quasar. There's some wiggle room, but I don't think, there's also a distribution here. Some of these objects, I think that needs to be understood. Some of these objects are shining for Salpeter times. Some of these objects are shining for
At least kind of bimodal.
Yeah.
Yeah, so I think we need to understand these short lifetimes. Okay, and I'm gonna come to that next.
You also get presumably a prediction for the number of dead quasars, right, from this.
So I know what fraction of the hosts are being populated. So if you want to call the other ones dead quasars. Those are these dark matter halos that aren't active quasars.
Okay.
So it's 1 minus the duty cycle, but the duty cycle is a fraction of a percent. Right? So most of them aren't shining, only 1 in 100 or so are shining. Okay, so one solution, I'm just going to go through the solutions and then we can discuss more. Okay, one solution is just like, look, just make the radiant efficiency 50 times smaller. Okay, and then you're good. So rather than 0.1%, let's make it, sorry, rather than 10%, let's make it 0.2%. And then the Salpeter time is down by a factor of 50, so it's 4 megayears. And then like, hey, we grow these quasars really fast. You don't have any problem with supermassive black hole growth anymore. We don't have to worry about massive seeds, problem solved. That's just, you know, we measured the lifetime, so we're good, right? That's one possible conclusion. Another possible conclusion is, which is testable, however, is that like, we're not actually, when we observe a quasar's rest ultraviolet emission, we're not actually observing the dominant phase of its growth. Like, it could be, and there are simulations that suggest this. I don't have the reliability meter on here, but they're not super reliable. Okay, but the idea is that like, actually, this is the ultraviolet emission. This is the actual total emission. And when two galaxies merge and you grow a supermassive black hole, the quasar is actually completely enshrouded in dust. Okay, it's a red quasar, it's extincted, it's an obscured quasar, and we don't observe it in the ultraviolet. And since all of the probes that I was telling you about, both the ionizing photon one and the clustering one, rely on observing ultraviolet bright quasars, maybe people would say, well, look, you're just not observing the dominant phase. That just happened again, okay. Sorry that I'm a little behind. So what's the dominant phase is this reddened phase, which we don't observe, and we're just seeing this UV bright phase, but like that could just be way shorter than the reddened phase. And like that's the solution. It's a possible solution. Okay, so like the obscuration that we're talking about here needs to vary in time, right? If the obscuration doesn't vary in time, then we're just observing the accretion disk for the total lifetime of the quasar and the black hole growth. So if you want to invoke this obscuration, it needs to vary in time. So there could be some obscuring medium that's dynamic. That would be one solution. So the blue here is when it's shining as a UV bright quasar, but the bulk of the time it's actually dust enshrouded. Another possibility is that it's just growing for some period in some cocoon when it's completely enshrouded, like the simulation that I just showed you. And then at some point it blows out and there's this short UV bright period. Okay, but then the key point is that like the ratio of time spent in each phase in a statistical sense is just going to be equal to the ratio of obscured quasars to ultraviolet bright quasars on the sky, right? So if you want to say that temporally they're only UV bright for a small period, then if I go out and do a sky survey, right, then there should be 50 of these obscured things for every one of these unobscured things. And that's a thing that we can directly test. We just need to find this luminous obscured quasar population. Okay, so then just to summarize, right, we observe the lifetimes to be much shorter than the expectation, right? And so you either need obscured growth, right, which is testable, right? You can just go out and find those obscured quasars and I can tell you whether it's commensurable with the lifetimes that we're seeing. Or you just need to accept that the radiant efficiency for these early quasars is a lot different than the naive expectation. Yes.
Well, I'll wait till then.
Okay, so then, but you got to be a little careful, okay? Because you can't do this at all times. Because if you do this at all times, you're going to break the Solton argument. Okay, so the high redshift distant quasars that I'm studying contribute negligibly to this integral. This integral is dominated by the peak of the quasar population, which occurs at sort of cosmic noon or redshift 2. Okay, so the picture then that emerges is like, look, you can play with the radiant efficiency or the obscured fraction at early times, but either one of those changes is going to change the left-hand side of this equation. And then that would mean that we were missing a bunch of black holes in the local universe, right? So you don't have flexibility at late times. It seems a little weird if accretion disks basically obey some physical laws. Why should they be different in the local universe than the distant universe? Okay, so the main point is that this change that we're finding cannot hold for low redshift quasars, which dominate the luminosity density. Okay, so then just to summarize, I talked about two different quasar chronometers. One using the neutral intergalactic medium, which catches every photon. The other using the clustering pattern of quasars on the sky, which leverages our robust understanding of cosmic structure formation. Both seem to require quasar lifetimes that are about 50 times shorter than the standard picture's expectation. So either the radio efficiencies are small or there's some unseen obscured population. Some of you may have heard that JWST is finding lots of obscured quasars, okay? And that might be this population that I'm talking about. I don't think that's the case. And I'm happy to talk about that during the questions, but I just wanted to mention that. And then these are the next steps, and I'm happy to now take questions. Sorry for going over time.
So you're saying that you can take care of this with like small epsilon or these obscure populations, but can you also take care of it with large seeds? I mean, how large would the seeds have to be in order to cut down your time by 50?
Yeah, so I guess what I would say is like,
There have been some large seeds found, right, with Chandra and JWST.
I don't believe any of the large seeds that anybody's claimed to find, and I don't actually think that you can actually convincingly measure seeds. Okay, so to me, the seed argument, the heavy seed argument is actually like our string theory, okay? It's some untestable thing that theorists like to play with, but there's no convincing evidence, in my opinion, for any large seeds. I'd be happy to discuss that with you offline. But so I'll say if the quasars are, if I'm actually only measuring a small fraction of the growth period, in other words, if there's this large obscure population, then, and you want to use a radio efficiency of 10%, then you would still need to invoke the heavy seeds, right? This light curve would just be dominated by the obscured phase. Okay, but I would also just say, like, why are you playing with the linear part when like you've got all this freedom on the timescales? I don't even know why people care about these large seeds. All you got to do is change this timescale by a factor of a few, and you remove the large seed problem entirely. Okay, but if I want to, but right, so if they're obscured, you might still need large seeds if you believe that the radio efficiency has to be 10%. Okay, however, if the lifetimes are actually that short, if we go out and look for the obscured quasars and we don't find them, and then you have to eat the radio efficiency of 0.2%, then like there's no more need for the large seeds because you can grow the black holes like super fast. So the seed problem just goes away. There's no need for large seeds. Now,
But you've got to find those obscure.
which I don't think is that difficult, right? But I mean, so JWST is going to help us do that, and also on my conclusion slide, the Euclid survey will help us do that. But we do need to find this population, and we make very clear predictions. They should be as luminous as the objects that we're looking at, and they should be clustered in the same way, because the clustering doesn't care if it's obscured by dust or not, right? I will say that there is another problem here that I'm glossing over, which is that now to form the supermassive black holes, if you want the radio efficiency to be this small, the accretion rate is now 50 times higher. So you now got to figure out a way to pack that much material, 50 times more material than before, into a small region. Okay, but my feeling is like, we don't have any way to measure the seeds. And I just showed you 2 ways to measure the lifetimes. So I don't know why everybody's so obsessed with the seeds. I think it's just because it's fun and it's easy. Yeah, sorry, did I make a very controversial statement? I do that sometimes. Yeah.
So I wonder about these predictions of like estimates of quasar lifetimes. Do we get any predictions on like how many young quasars should we see? Like those, I mean, we can kind of try to find an observation that if we're looking at radio loud ones, we can start like just those that start launching jets and stuff like that.
Right. So, and we also see some young quasars, right?
Yeah.
So I will say that this analysis, we've done this more carefully before, but I will say that like, it's not really clear. If I go back to this slide, right? So a young quasar could be that there's just some light bulb that's characteristic, and then you happen to get lucky and observe it when it just turns on. Okay, and so a more careful analysis would factor in, this is the intrinsic lifetime, but what you actually want to know is like the age, which is like how long has it been shining since I observed it, which is different than the actual light bulb lifetime. Okay, so I think that within this framework, we can try to understand the young quasars, but
Just predict how many we should we see.
Right, and so like roughly, for 10 to the 4, if the lifetime is 10 to the 6, you expect about 1% of them to be young if they're turning on. It doesn't change the answer that much because like the age and the light bulb are basically roughly within a factor of 2 each other.
Mm.
But like, yeah, so 1%, and I think we're seeing more than 1%. I think we're seeing like, a few percent. So maybe there's not a problem there.
So if you are seeing more than expected, then the lifetimes are shorter.
It could also be that there's a distribution of lifetimes and distribution of radiative efficiencies, right? So, or it could be that because of this variable obscuration, you sometimes see them when they just got cleared. So I don't actually, it's a good question. You had a question?
Oh, I just kind of going, not my area of expertise at all, but just going back to your previous statement. You're saying, okay, maybe it's much easier than trying to have heavy seas to just grow them faster, but then you just offhandedly slightly mentioned the idea of having to pack more material. Then is that hard? What are the things you have to start to ask to determine how hard that problem is then?
I
Answer
think
that question.
Yeah, so I think that you would need to, so that's ultimately a question of fuel supply. And what was I gonna say? So it's a question about the fuel supply, and most calculations just presume that the fuel supply has to do with the cosmological fuel supply, which isn't at all clear to me that that's a good assumption. So here's a simple example. You need about 1 solar mass per year to grow a 10 to the 9 solar mass black hole in 1 gigayear. Okay, so you can actually do that with just winds from massive stars. If there's a star cluster around the around the supermassive black hole, just stellar mass loss can give you 1 solar mass per year. That has nothing to do with the cosmological, environment. I mean, you had to form that star cluster, right? So now you could ask, can I get 50 times more mass, right? But I think that's a very interesting problem for study. And I will say that most calculations are just assuming that it's cosmological and they're running cosmological simulations, but it's not at all clear that that's the right scale to simulate. Does that answer your question? Yeah.
So you said that I think the two from you said you don't think the JWST obscured quasars are going to be the ones you're looking for. Why?
Yeah, it's a good point. I'll just show you quickly. I think it's not, I think the vote's a little bit still out. But one is that I just don't believe that a lot of those objects are actually luminous AGN. I think there's a lot of galaxies mixed in there. But so the main answer is that, like, if you use the number of objects that JWST is finding that they claim are as bright as the quasars that we're studying, you just break cosmology. Like, there's no way that there's just too many of them. And so, like, there's no dark matter halos to host them, right? But you could make them, they could be here, right? So cosmology allows them to be here, but then that's not the population we're looking at. So I think it's doable with a combination of JWST and wide field surveys that we could find this population, but I don't think that the population of objects that people have been studying with JWST, I'm not convinced a lot of them are actually black holes at all. I think there are a lot of galaxies in there, and you have no idea how bright they are. So that problem needs to be solved. So this commensurability with the bright quasars is making some assumptions. So, this is the analysis, but the JWST AGN are here, quasars are here, and this, you might think, okay, well, that's that 50 to 1. It's actually 1,000 to 1, but you don't really know where they are in terms of luminosity. They're making a lot of assumptions there.
And my second question is, and this may be showing my ignorance, but can eRosita help you at all?
It's probably not. eRosita is not very sensitive to these distant objects.
Okay.
I think eRosita could help you find obscured quasars at lower redshift, which would relate to the Sultan argument that I talked about.
Yeah.
A lot of that's been done already by Chandra and Spitzer, etc.
Okay.
But the other thing is that eRosita is soft, and you can have Compton thick AGN, so
Okay.
you really want to work harder.
Okay.
Yeah, that's a good question though. Yes.
It's slightly different, but can you go back to one of the slides where you have the believability-ometer?
Yeah. Which one? I'm in
It
trouble.
doesn't matter which one.
Okay. I'm busted.
No, you passed one.
Yeah.
Okay. I just want to point out, I want to point one thing out and then ask something. So I would have thought that yellow would have been like the flat face. Like, because the middle is like, I'm still happy, but I would have thought that the orange face would have been where the yellow one was, and you would have two successively more
Yeah.
frowning faces going on, so there could be a bias here.
We take it.
Okay, and the other thing was, I thought at the end, what you were gonna do is you were gonna count up all the reliabilities,
Uh-huh,
and then somehow show that the areas that you were concluding
uh-huh.
were more reliable than, let's say, other areas. So in other words, these were useful signposts, but I thought it was gonna be more of a tool.
Yeah,
And to go to the end to say, you see, like, this chain of argument is actually more reliable than that chain of argument.
yeah, it's I was trying to do that. I was trying not to be too mean, but basically,
Well, you haven't shied away from. Well, why start now?
fair enough. So, if I go back to, is that your question, by the way?
What? Why are you mean?
No, you said that you had a comment and a question,
No, the comment was
the reliability
the
meter.
flat face should be in the yellow.
Yeah,
And then the
so,
question was,
what,
are there, can you use these reliability meters to say this is more reliable than that?
yeah, so what I guess, I don't want to diss the simulations because they're a very valuable tool and they build intuition. They help us understand what kind of observations to make, where to look. And I'm also working on these simulations, right? But I guess we want this ab initio picture, right? But then built into that are like a lot of assumptions. And then, so the theorists are convinced that we have to have these heavy seeds, right? And they're building this on what I would call a set of unreliable assumptions, okay? And so what I was trying to do with the reliability meter, which maybe I didn't effectively get across, is that I was trying to make the case that, like, look, the conclusions that I'm making about lifetimes are just basically rooted in simple physics and cosmology that we really understand well. So I think that those conclusions are reliable. And then a counter argument that people would make that maybe are in this camp, they would just be like, yeah, but you're just observing this irrelevant part, which is the UV luminous part, and that it's all obscured, and that we need the heavy seeds. But I think that hypothesis is testable because we can go out and look for the obscured quasars. But I think the main thing I was trying to get across is that I think that the lifetime estimates are robust. Okay, we still need to integrate these constraints into those kinds of models. But right now that's not happening. People are obsessed with the seeds. When I think, why do that? Why be obsessed with the seeds when we can directly measure the timescales? Maybe they're not the relevant timescales though. Maybe the obscured phase is the relevant. I don't know if I answer your
I
question.
think your position on seeds is pretty.
Yeah.
So we're quarter past. Are there any really burning ones in the Zoom?
There's no questions.
Okay, in that case, I think we should call it so people can eat their festive holiday lunch at the. Just remember to please sign up for dinner.
Yeah, I wanted to say free was on. I'm trying to cover for free.
Yeah, I was good.